It's a pleasure to have Omri Weinstein give the first talk today.
Thank you. Hi guys, good morning. So this is a joint work with Sasha Golovnev and Zev Dvir. So I know Sasha gave this talk in the previous workshop, so I apologize if a few of you need to hear some of it again. It was a shorter version of the talk. On the upside, we have a kind of a significant new result, which was proven only the kind of last 2 weeks, which is why the paper is not out. So hopefully it will contain some new things towards the end. All right, so this talk is going to be mostly about data structures. So data structures. The data structure is basically just a compact way to represent or encode information in a database so that queries about the underlying data can be answered quickly. In the static data structure model, we are given a database of n elements, and this could be essentially anything you can think of: n-vertex graph, n-bit string, set of endpoints in some high-dimensional space. And you need to pre-process this data that I gave you in advance into kind of cheap memory, S-memory cells, such that each query from a predefined set of Q queries, so let's say n-cubed queries, needs to be answered by few memory accesses, kind of with few IOs. One important example is the orthogonal range counting problem, where the database is just a collection of endpoints in the n squared planar grid, so there are n squared points on this grid. And the query is just a point on the grid which defines an axis parallel rectangle. And the goal is to report the number of points in this rectangle. So let me save you the marketing pitch for why this problem is important. This is kind of so Amazon needs to solve this problem on a daily basis. And this is a really fundamental problem in computational geometry databases. So any such problem admits kind of two extreme naive solutions. One of them is kind of to cheat and store all the answers. So the query time, of course, will be optimal, right? You just read off the answer. But the space, unfortunately, is kind of big. You need to store all the queries. And this n squared can be easily like n to the 10. So typically we have a polynomial number of queries. The other solution is to do the opposite. So no clever preprocessing. So you just store the database in the raw. No clever encoding, no nothing. And of course, the space is optimal, right? Any non-degenerate data structure problem, you have to store at least the input data. Otherwise, all bets are off, right? Unfortunately, though, the query time, because you didn't do anything clever in preprocessing time, you will just have to, there's nothing better you can do than just a linear scan, so the query time will be linear. Does that make sense? And of course, the natural question, is there anything in between, right? So can we do anything more clever that trades off the time and space? And static data structure lower bounds aim to quantify this trade-off by proving unconditional lower bounds on a trade-off between time and space. Right? Okay, so we want to prove lower bounds. We need a model for data structures. And kind of the most compelling model for proving data structure lower bounds is the so-called cell probe model, which is is a very kind of crude abstraction of what a data structure actually is. It basically views a data structure as just a table of cells plus a decision tree or a query algorithm. More formally, an ST data structure in the cell probe model is just a pair of kind of two objects. One of them is a preprocessing function that takes your input database of size n and preprocesses it into S memory cells. And this preprocessing function is completely arbitrary. So, you can literally encode anything you want, no computational constraints, no nothing. Anything you want using S bits of S memory cells. Each cell typically contains log n bits of information. And the reason why the word size is usually log n, is because you want to at least be able to index an element in your database, and you want to at least store a pointer to some other memory cell. So it's usually log of n, which is roughly log the number of queries, because the queries are in a polynomial in n. That's the setup. The second object is just, okay, once you have this memory state of the data structure, the query algorithm specifies for each query a set of at most t memory cells that reading those cells will retrieve the correct answer for the jth query. So far, so good?
So is it adaptive or non-adaptive?
Sorry?
Are they adaptive?
Good. So in general, the query algorithm is a depth T decision tree in the adaptive model. But if the data structure is non-adaptive, which will be the focus of this talk, then it's literally a depth 2 circuit with of width s. So the middle layer is of width s, which is larger than n. And the top fan-in, though, is very small. It's maybe PolyLogarithmic or something. So it's kind of a very specific model of depth 2 circuits. The main point is that the bottom gates are unbounded fan-in and completely arbitrary, kind of both at the top and the bottom. Questions so far? All right, so that's a cell probe ST data structure. And this model is kind of extremely powerful in the sense that it renders time-space trade-offs completely an information theoretic question. There's no, it's a non-uniform model, so there's no, absolutely no computational constraints. And kind of the claim to fame of this model is that it literally captures any data structure, lower bound that you can imagine, regardless if it's, whether it's implemented with a C++ or Java code or on some Intel compiler and so forth. Since the gates are arbitrary, this model is non-uniform. It literally doesn't care about any computational constraints. So all computations on probed cells are completely free of charge. All they care about is how many cells you store and how many IOs you have. All right? That would be important. Unfortunately, not surprisingly, this abstraction also makes it very difficult to prove unconditional lower bounds on data structures. And more specifically, even though most data structure problems, so a random data structure problem with polynomially many queries, there's kind of nothing better than you can do than either storing all the answers, or probing all the cells. So kind of for a typical data structure problem, there's nothing better that you can do than just the naive extreme solutions. Just kind of very. Actually, the bound is much stronger. You need like m to the 1 minus little o of 1. So it's really nothing better you can do. In contrast, we know that for many data structure problems, we do have these incredible data structures. And in particular, the highest explicit lower bound we have for any data structure problem with polynomially many queries is the following bound. It's log the number of queries, which is m is like n to the 10, so it's like log n, right, over log space over n. In particular, if you want to prove lower bounds against linear space data structures, which use 10n space, you get a logarithmic lower bound, and this is kind of the record so far. It was proven. I mean, okay. The good news is it was proven for kind of not just contrived problems, but for like problems we actually care about. So Casper proved it for polynomial evaluation problem, for range counting problem, for near neighbor search, maybe up to a log n loss in the query. But so we have this lower bound for kind of problems we care about. So unfortunately, there's no higher subprobe lower bounds, even for non-adaptive data structures. So we don't know how to separate adaptivity from non-adaptive data structures in the static model. This is kind of in sharp contrast to the dynamic model. So the role that adaptivity plays in the dynamic model is crucial, kind of, and maybe not very surprising because the data is online. In the static model, beating this lower bound asymptotically would be kind of a real breakthrough, even for non-adaptive data structures. Questions? All right, so given the, the difficulty of proving self-probable lower bounds, a natural and kind of intermediate milestone, similar to the circuit complexity and lower bound enterprise, is to consider restricted model data structures. And indeed, over the years, several restricted model of data structures were considered, such as the pointer machines, the word RAM model, and some algebraic models, most notably the linear group model. So since linear queries are kind of very ubiquitous and important, this model received quite a bit of attention. So a linear data structure problem is nothing else but just a matrix, an m by n matrix. And the input database is just over some, your favorite finite field, f. The input database is just a n-bit, n-letter string, so an n-dimensional vector x. The queries are specified are just the rows of this matrix, right? So we have m, maybe n to the 10 queries. And the answer to the jth query is what you would guess is just the dot product between the jth row and the data. Right, so does it make sense? So this is a linear data structure problem. An ST linear data structure is what you would think is just restricting the gates of the circuit to being linear, similar to kind of arithmetic circuit. And so a linear data structure can store S elements of the field F. So basically S linear functions, but we will see this is kind of without loss of generality. The important thing is that the query, right, so the top layer of this circuit needs to answer each query with a t-sparse linear combination of those memory cells. So it's a nice exercise to show that if the top layer is linear, you can for free linearize the bottom layer. So this is actually not a real constraint. It's a nice exercise to prove. And yeah, so linear queries are kind of an important special case. So the range counting problem we saw in the beginning of the talk is a linear problem. One way to see it is that the database, the endpoints are just the indicator vector of dimension n squared, and they indicate 1 wherever you have a point. The rows, the queries, are just the indicator vectors of the rectangles, of all possible rectangles, right? And then you just compute the dot product. It counts the points inside the rectangle. Makes sense? You can of course imagine non-orthogonal range counting problems where you have balls or triangles instead, and these are conjectured to be hard. So linear data structure problems are both interesting and kind of non-trivial to solve. So the partial sum problems, just an example, another example is just the lower triangular matrix. Polynomial evaluation is just a Vandermonde matrix. What else? Dictionaries are just the identity matrix. So we have natural spatial case, and the saga goes on. So kind of we have no higher lower bounds than this log m over log space over n, even for non-adaptive linear data structures. So somehow, even in the group model, we don't know how to beat this bound. And once again, this is in sharp contrast to the dynamic online model. There, so Casper has a nice paper where we can prove actually polynomial, definitely PolyLogarithmic, but even polynomial lower bounds on the query or update time. So this shows this like a real big difference between kind of the static and dynamic model. In some sense, this is one of the messages of this talk, I guess. In particular, there's no super logarithmic lower bound even against linear space. So kind of this is kind of the first thing we would try to prove, right? We restrict the data structure to store 100 cells of memory cells. Right, and okay, before we present the result, kind of at a very high level, one of the main messages of this talk, that this is kind of not really a coincidence, that it's not a coincidence we're stuck here. In some sense, a logarithmic improvement, or in other regimes, even any asymptotic improvement, even against arbitrarily small linear space. So even if you restrict the data structure to store, 1.000001 memory cells, it seems like an easy case for a lower bound. Even then, this would imply kind of breakthrough results in complexity.
Even more breakthrough than this.
Then?
Even more breakthrough than this.
Yes. Yeah, well, depending on how much you care about rigidity. It's a different enterprise we can debate. Yeah, so I should say before, I kind of getting ahead of myself, but I should say in advance that this will not be, a complete no-go theorem for data structure lower bounds, in the sense that proving polylogarithmic, let's say log to the 10 query lower bound against linear space, will still not nearly get us to circuit lower bounds, which is kind of on log depth circuits. We'll get to that. So kind of don't despair already. We will see that only if you prove we'll see this in the end, only if we prove extremely strong data structure lower bound, only then will it actually imply kind of circuit lower bound. So there is kind of some hope. I think the main message is basically a new connection between two computational models. That's the main message, and maybe somewhat of a sign that, yeah, dynamic lower bounds are easier to handle. But yeah.
Dynamic, they imply static, right? For many settings, if you prove like more than log square n for dynamic, you also have static lower bounds. You mentioned this thing to me yesterday.
Depending on the problem.
For many problems.
For
range counting, you get
I mean, for composable problems like range counting, yeah, we can, if you prove it with a certain chronogram technique, but yeah, so we can discuss this. But yeah, that's a good point. All right, so one observation, kind of to set up the stage for our result, is that an ST linear data structure for a linear problem M is nothing but just a factorization of the input of the data structure, the problem, into a product of a sparse matrix, right? A T row sparse matrix, which has T non-zeros in each row, times a small matrix. So this matrix can be completely arbitrary, but it's narrow. It has only S columns. And if you don't see this immediately, then maybe one way to see it is that a linear data structure only needs to be correct on the basis, on any basis, right? So you can think of the ith column of this narrow matrix as just encoding the memory contents of the middle layer if the input database was the ith basis vector, right? So we have all the memory contents of the basis vectors. And now to answer the jth query, the jth row, the data structure specifies T non-zero entries that it wants to read from each memory, right? Does that make sense?
So I think you mentioned earlier that the reconstruction is linear without loss of generality, right?
No, the other way around.
Oh, the other.
If the reconstruction algorithm is linear, then the middle layer, the pre-processing function is linear.
I see.
And it's a nice exercise, actually.
Okay.
So we assume both are linear, but actually you only need to assume that this is. Does that factorization make sense? Questions about that? Right, so the space of the data structure is just the number of columns or the number of rows of this matrix. So each row, the original query needs to be expressed as a sum of T rows of this matrix. These are all equivalent. All right, so what does it mean to prove a linear data structure lower bound? Just finding a matrix which cannot be factorized as a sparse times small matrix. Make sense? Great, so linear data structure lower bounds correspond to finding matrices which do not admit such factorization into a product of two matrices, one of which is sparse. In contrast, the problem of matrix rigidity is the problem of finding a matrix which cannot be factorized into the sum rather than product of a t-sparse plus a low-rank matrix. So kind of informally, a matrix, an m by n matrix, is rigid if it is t far in Hamming distance from any low-dimensional subspace or from any low-rank matrix. Maybe one useful, more geometric way to visualize this is that a matrix M is RT rigid if for any low-dimensional, for any r-dimensional subspace L, there exists one row, one of the points, one of the rows in M is t far away from the subspace in Hamming distance. Make sense? This is, L is just a column space of this low-rank matrix. Right? And I do want to stress that, okay, so what does it mean for a matrix to be RT rigid? Yet another way to view it is that you need to change, you need to modify T entries in some row of the matrix in order to decrease the rank from what it originally was, which was N without loss of generality to R. All right? And I want to stress that this is kind of a worst case notion of rigidity. The somewhat more standard notion of rigidity is actually 10% of the rows are actually far from any low dimensional subspace. So global rigidity or average case rigidity is what seems like a much more powerful notion. And towards the end of the talk, we'll see that actually, this is one of our main new results, is that they're actually equivalent up to a logarithmic loss in sparsity. So I'll get to this later, but I want to stress this notion of row rigidity or worst case rigidity is going to be important to the results we'll state, but will cause us some problems later that we will show how to fix. Right? And finally, I want to define this notion, which will not play a major role in this talk, but so it's just for kind of purpose of nice characterization. A matrix is strongly rigid if it's rigid in any basis. So no matter which basis you choose for the matrix M, it's still hard to reduce the rank. And this notion kind of only makes sense for rectangular matrices, right? For square matrices, you always have the standard basis, right? So there's no hope to prove that. But if this confuses you, just forget about strong rigidity. Just it will not really be used.
Sorry, what do you mean by the matrix in any basis?
So this property of this decomposition is in principle, it's the property of which basis you choose for M, right? Which basis you choose for your original matrix. And strong rigidity means that, okay, so think of a n squared by n matrix. It's just, you can view it as a low dimensional subspace in F to the M. Maybe it will be clear later. And I let you choose any basis you want for this low dimensional subspace.
For the rows, is that what you're saying?
No, I'm saying maybe it will be clear in a few slides. So maybe we can.
You allow changing to a similar matrix? That's what
Sorry?
you're saying? You can change just to any similar matrix?
What do you mean? So
are you multiplying M by unitary?
Yes,
by unitary
exactly,
matrices and saying all of them should be rigid?
yeah, exactly. So I am saying that, yeah, so for square matrices it doesn't make sense because you can always transform it into the standard base, right? It's an n-dimensional subspace in F to the n, so it doesn't make sense. So this is the type of discussion I didn't want to get into because it confuses you and it's not going to be important. But we can talk about it. It will be clear in very soon. You can forget about strong rigidity for now. I think it would just confuse you. For the experts, we can. So just a 2-minute motivation for why we care about rigidity and what are kind of the holy grail parameters. So by the way, in rigidity, we always have two parameters. There's the rank parameter and the sparsity parameter. So this is going to be quick. If you don't, if you're not familiar with this motivation, then it's fine. It's not going to be necessary to understand the talk, maybe only the last few slides. So the main motivation for studying rigidity is proving superlinear lower bounds on logarithmic depth circuits. And it follows from like a really nice reduction proposed by Valiant in 1977. So kind of all of our shrinkage-based techniques completely fail for logarithmic depth circuits. We don't know how to handle log depth circuits in any way except this one very nice program developed by Valiant. So what Valiant showed is that if you have a logarithmic depth linear size circuit, so in particular it computes, at most 10n outputs or something, then if your function is computed by this logarithmic depth linear size circuit, then you can translate this circuit. It is also computed by this depth 2 circuit, which is of somewhat very different kind than the data structures. So it's a depth 2 circuits where the middle layer stores actually not larger than n, but fewer than n. It's like n over 1,000 bits of information. And each query, so the middle layer stores, so it computes the same function that the original circuit computes. But the middle layer now stores n over 1,000 bits, so it cannot possibly store, you cannot recover the answers to all the queries just from this middle layer, right? Because it stores less than the input, less than n. So the queries must be connected also to some of the inputs, right? So the picture is like this. Each query needs to be answered as a function, of two objects. One is those n over 1,000 common bits, which are completely arbitrary functions of the inputs and can be viewed by any one of the queries, plus a very small set of n, n to the 0.1 inputs, which are hardwired to the query. Makes sense? And what Valiant showed, and this is a really nice observation, is that if this circuit further computes a linear function, a linear transformation, similar to the data structure story, so these are just the answers to each row of m, then this linearity actually induces a decomposition of the matrix M into the sum of a sparse plus low rank matrix. I'm not going to explain this, but you can see this. The sparse factor B comes from the fact that each query reads only n to the 0.1 input elements. And the low rank part comes from the middle layer, right? It's low rank just because it has dimension n over 1,000. So this is all I'm going to say. So the point, if this didn't follow, then the main point is that if a linear circuit computes your linear transformation M with linear size and logarithmic depth, then this reduction, which is completely combinatorial, but if you apply it on linear functions, then you get a decomposition of M into a sparse plus low rank matrix. And the corollary is that if we can find an explicit matrix such that to reduce its rank from n to n over 1,000 requires modifying n to the 0.1 entries in some row of the matrix, then the corollary, the contrapositive, is that it cannot be computed by linear size log depth circuits. Make sense? So if you didn't follow this, then you can stick around this motivation. The main point is that kind of the holy grail parameters we care about is linear rank, or maybe even n over log n, but let's say n over 1,000, and polynomial sparsity parameter. So try to keep this in mind. This is kind of very strong parameters, and the matrix needs to be nearly squared. So we'll talk about this soon. All right, so what do we know about rigidity lower bounds? Not surprisingly, a random matrix is extremely rigid. So you need to, even to decrease the rank below n over 2, you need to modify like n over log n entries in the matrix. So in each row, sorry. Once we go to explicit constructions, once again, the situation is kind of very gloomy. So the best lower bound we have, if you want to decrease the rank to r for any parameter, rank parameter r, you need to change roughly n over r times log n over r entries, which is a mere constant, like 10 for square matrices if we want to decrease the rank below n over 2. Right? And yeah, so since we were so bad at proving square matrix rigidity, one nice program proposed by Alon Panigrahi and Yohanin about 10 years ago is that, okay, fine, if we're so bad at proving square rigidity, let's try to prove rigidity lower bounds on rectangular matrices, which is kind of matrices with, again, n to the 10 rows. And Intuitively, this should help. Remember, a matrix is rigid if one row is far from any low-dimensional subspace. So if I give you a list of n to the 10 rows, this should only help, right? I mean, I'm giving you a budget of more potential vectors, and you need to fight against all low-dimensional subspaces. So this makes kind of sense. And indeed, they show that you can get some slightly better results. So you can get rigidity of log m over n for a matrix with polynomially many rows. More specifically, for any parameter d, they give an explicit construction, a very simple error-correcting code construction that has n times 2 to the d rows. So you need to set d to be logarithmic for this to be polynomial. And in order to decrease the rank below n over 2, you need to change at least d entries in each row. All right, so this is restated in this. But for polynomial m, this will never give you better than log n, right? So this recurring barrier or frontier of log n is kind of the main theme of this talk. So remember, this is like extremely far, even forget the square versus rectangular. This is a kind of extremely far from the Valiant's program, right? Valiant wants n to the 0.1, the number of entries you need to modify to be like n.1 to the 0.1. So it's just like still extremely far. But this is the current frontier to kind of beat. And yeah, so kind of the summary so far of the talk. So everything we discussed is that rigidity lower bounds amount to finding explicit matrix, rectangular matrix possibly, that cannot be factorized as the sum of a sparse plus low rank matrix, whereas data structure lower bounds in the group model amount to finding a matrix which cannot be decomposed as the product of a sparse plus small times small matrix. Make sense? Yeah, so kind of maybe syntactically you see some differences. Of course, semantically these factorizations are very, very different, right? So it's not clear how to relate these two things. And maybe probably the key kind of the key observation or the key point of view for relating these two factorizations is to look not on the row space of the matrix, not on the rows, but actually as on the column space of this matrix M. More formally, we want to view M not as a set of n to the 10 rows in f to the n, but as a low-dimensional, n-dimensional subspace of f to the m. So it's a very small n-dimensional subspace inside f n to the 10, right? So make sense? Did that make sense? So let's look at M. M is a M. Capital M is is a little m by n matrix. We can look at its column space. So it's just an n-dimensional subspace in f to the m. Because we assume the matrix is kind of full rank. And we say kind of the key definition here in this talk is the following. We say that a subspace in f to the m is T sparse if it is the column space of a T row sparse matrix. It's a little weird, but it will be important for us. So is this parse? So
this is a property of subspaces, but there's an existential quantifier on the basis now.
Yeah, so right now we will. Okay, so this is a property of subspaces which has nothing to do with the basis so far.
If there exists a basis which is
yeah, exactly. So another way of saying it is what Madhu said. A subspace is T sparse if there exists a sparse matrix, matrix A, which has at most T non-zeros in each row that the column space of this matrix generates this subspace. All right, this will be important. Now we make the two key definitions of this talk. The inner dimension of a matrix M is the largest dimensional intersection that your original matrix M can have with any T sparse n-dimensional subspace. So here's the game. I give you, look at M, look at the column space of M. In general, this is an n-dimensional subspace in f to the m. right? But it's very non-sparse. So think of the Vandermonde matrix or something. It's not generated by a sparse matrix, for what we know. And the game is the following. I give you a budget of n dimensions, but you have to generate it with a sparse matrix, and your goal is to cover as much as you can, to intersect the original subspace as much as you can. And the inner dimension with sparsity parameter t is just the largest dimension of such intersection. Questions? The outer dimension of the matrix, denoted by capital D, is the minimum dimension of a t-sparse subspace that doesn't only intersect, but it actually covers the entire matrix. So now the game is different. Now I force you to actually contain the entire space, which is not sparse, so you have to pay some more dimensions, right? But now I force you to actually contain the column space of your non-sparse. Is that clear? So in the next 5 minutes, I want to convince you that, and this is kind of the key fact that makes the rest of the results, or at least most of them, kind of fairly simple. I want to convince you that the property of being rigid, or strongly rigid actually, is exactly the property of having low inner dimension, and the property of a matrix okay, so a matrix is rigid if and only if it has low inner dimension, and a matrix does not admit, does not admit an efficient data structure, so it has a data structure lower bound if and only if it has large outer dimension. So that's the goal in the next 5 minutes.
And you will relate inner and outer later?
Exactly, exactly. So the whole connection will come throughout relating these two notions. Exactly. Okay, so the first lemma, which is it's a simple lemma, but it's somehow the key to at least most of the result, is the following. So I claim that a matrix is not rigid if it is sparse on some large dimensional subspace of its column space. All right, so we're going to prove that a matrix is not epsilon and t rigid, so you can decrease the rank below epsilon n by modifying only t entries in each matrix. This means that the matrix has to be t sparse on some large n-dimensional subspace, which exactly means that the inner dimension is large, right? I mean, that exactly corresponds to the inner dimension being large. Like, lemma makes sense? All right, so suppose your matrix is not rigid, so by definition it admits a decomposition into a sparse plus low rank matrix. And note that because rank is subadditive, then the rank of A, right, must be very high, because M is without loss is full rank. It has rank n, right? B has low rank, so A has to have rank at least. So now let T be the linear map, the linear transformation, whose kernel are precisely the columns of M. We can always construct such linear transformation, right? I just put all the n columns of M in the kernel and just extend it to the basis. Now take this linear transformation T and apply it on both sides of this equality. So what will happen to the left side? It will zero out, right? Because the kernel is precisely the column space of M. So we get that, by switching sides, that T minus TA equals to, should have been a T, not that. So do you agree that the rank of, in particular, the rank of TA is equal to the rank of TB? Questions about this? Right? Okay, so let's think about it. So, and we know that the rank of TB cannot be more than epsilon n, right? Because rank is submultiplicative. You cannot increase the rank by multiplying by a matrix, and the rank of B was very small, was epsilon n. So how could it be that the rank of TA is small? A had very large rank to begin with. The only way it can decrease to below epsilon n is if it had a very large intersection with the kernel of T, right? If it has less than 1 minus 2 epsilon n intersection, then the rank will remain larger than epsilon n. That would be a contradiction, right? Is that clear? Right, so it's a simple claim.
So where was the sparsity now? Where do you get the sparsity of A?
So the point was that the column space of A, by definition, are sparse. So we kind of used it to kind of a black box, but it was crucially used. All right. So, and actually, you can prove the other way around. So this only used rigidity, standard rigidity. For the other way around, if you think about it, you cannot prove it. If you want to prove this for the other direction, you have to use strong rigidity because it's not a property of the base. It has to be, for any basis, right? Because it's a property of subspaces. But we're not going to. We're only going to use this lemma. So let's call this lemma star, and this is the only direction we'll use. I should say that Paturi and Pudlak already essentially they defined a subtly different notion of inner and outer dimension, and they proved the non-trivial direction in a somewhat different argument. So it was hidden in some Russian journal paper they wrote. So it's actually slightly different, but they already essentially observed that. All right. Okay, so hopefully you convinced ourselves that a matrix is rigid if and only if its inner dimension is small. Now I want to convince you that a matrix does not admit, a matrix admits an efficient data structure, an ST data structure, linear data structure, if and only if its outer dimension is small. So in other words, we have a lower bound if the outer dimension is large.
The previous statement was not an if and only if, was it? It was just a one-way, right?
It was strong rigidity.
For strong rigidity, you can prove the other way around. It's actually easier. It's the trivial kind of direction. But we won't use it, so it's just for the characterization. How am I on time?
15, 20 minutes.
Really? Okay. So we'll have to go a little faster for me. Okay. So this is nothing more than just an observation. I claim that, right? So if a linear problem admits a linear ST data structure, it admits this factorization, which means that. So this factorization is exactly the low-dimensional subspace that contains the matrix, and you can see this. Just what does that factorization mean? It means that every column of M is generated by the column space of A, and B is just the linear combination encoding this factorization, right? Is that clear, right? So I claim that the column space of A must contain M, and B is the evidence for that, right? B just specifies, remember, B, there's no sparsity constraint. B just specifies the column, the linear combination of the columns that produce the column space of M. That's it. So I'm not saying anything very interesting. So, okay, so you took a nap. This is kind of the time to wake up. So everything we discussed boils down to that kind of statement. So a matrix admits an ST linear data structure if and only if its outer dimension is at most S, and it's strongly rigid if and only if its inner dimension is small. So in that terminology, what does it mean to show that a linear data structure lower bound implies a rigid matrix? It's essentially equivalent, as Madhu proposed, to showing, to understanding the relationship between inner dimension and outer dimension. In particular, it means if we can show that large outer dimension, which is a data structure lower bound, implies small inner dimension, then we get this implication that we want, right? So showing that data structure lower bounds imply rigidity is equivalent essentially to showing that large outer dimension implies small inner dimension, just by this characterization.
The other way around is just clear now. Rigidity implies the data structure.
Okay, so that's true only for very weak data structure lower bounds against linear space, but I agree, that's a simple implication, which I probably won't have time to discuss. So yeah, so the other way around, this is also true, but only kind of for kind of weak data structure lower bound. If you can prove rigidity, any type of rigidity, you only get a lower data structure lower bound against 1.01 in space. But yeah, discuss this later. So let me try to discuss this in the main kind of framework or result. So this is essentially exactly what we show, right? So we show that if you give me a matrix whose outer dimension is large, so it's more than 1.01 n, then we can actually find a submatrix, right? And this submatrix whose outer dimension with a loss in sparsity of log n is small, is less than 1 minus some epsilon prime n. Which exactly means by this characterization that this new matrix M prime is epsilon n t over log n rigid, right? Right. So if you can ignore the parameters, but morally speaking, this is what's going on. And moreover, this matrix, so we cannot make the proof exactly explicit. This matrix can be found in using an NP oracle, but this is still far beyond any kind of circuit lower bounds we know. So as far as circuit lower bounds, p to the NP constructions are considered pretty much explicit. So we don't know how to prove circuit lower bounds even against much higher non-deterministic classes. So and the corollary is that superlogarithmic, any superlogarithmic lower bound on data structures, linear data structures, would give you something non-trivial about rigidity. In particular, if you prove a polylog and query time lower bound on any linear data structure problem, even against 1 plus epsilon 1.01 space, which seems like not too much to ask, then you would improve this APY construction by the same polylog factor minus 1. So in particular, if you give me a superlog squared data structure lower bound in the group model, you would improve the APY construction, right? But only for rectangular matrices, and hopefully I'll have time to show the implications on square matrices. All right, so does everyone kind of agree with this corollary, right? You lose one log factor because of this. And I want to say that this kind of indicates a threshold result in data structure lower bounds, because for succinct data structures, if I constrain the data structures to use not n to n, 1.01 n, but actually n plus little o of n plus root n space, then we actually know polynomial cell probe lower bounds. Then we kind of have almost everything we want. And this shows that once you go to linear space, arbitrarily small, all of a sudden lower bounds become extremely powerful and hard to prove.
So how explicit is this now? I mean, because there is for all m there exists an m prime.
Yeah, I say so. Let's just very quickly sketch the theorem, the proof. So the proof says the following: give me your matrix for which you have proved the data structure lower bound. So you prove that the outer dimension is large, is at least, but not terribly large. You only need to convince me it's larger than 1.01 n. I will show you, I'll give you a p to the np, so a polynomial number of calls to an np oracle that will produce you a submatrix of this matrix, which is log n, which is rigid with those parameters, right? And now you can, the algorithm is not very difficult. It's kind of a simple recursion once you have these definitions in hand. So let me give a very quick sketch because I want to get to the second result. So you start with your matrix, right? M by n. If it's rigid already, which you can check with an NP oracle or kind of co-NP oracle, then you're done, right? That's fine. If it's not rigid, what does it mean? If its inner dimension is small, then by definition, lemma star implies that there is some large sparse, T-sparse subspace that intersects a large fraction, 1 minus 2 epsilon of its column space, right? This is exactly the implication of a non-rigid matrix. It's sparse on a very large subspace of its column space. All right, great. So kind of the idea is, we're working in the contrapositive fashion. Suppose it's not rigid. I will gradually construct a too good to be true cover of the entire column space, and that will contradict the fact the outer dimension is small. I will cover it with too few dimensions or space. Okay, good. So we're done with like half of the columns. So and the nice thing is that, right? So this is exactly what it means that A covers this fraction of the column space. And the good news is that, remember, the lemma says that we managed to cover this fraction using a very cheap. We paid for it only n dimensions, right? And we have a budget of 1.01 n dimensions. So we paid for it only. We have, 1 plus epsilon n dimensions to afford, and we only paid n dimensions out of it, and we already covered like 70% of the column space. That's kind of great news. And now what we can do is we can just extend this matrix that we found just greedily, right? Just greedily with epsilon n, 2 epsilon n columns to form a basis of the original M, and we just recurse on the remaining part. So I want to get to the next result. So there are other ways you can perform this reduction. You can fine-tune the parameters. But the basic idea is that why do we lose this log n factor in sparsity? Because in order to cover the entire matrix, it shrinks by a constant factor each time. So you need to pay like log n iterations. In each iteration, we find a sparse subspace that covers another constant fraction of the remaining rows, and the sparsity increases by t, right? Because we add up those matrices in the cover. So this is why we absorb another log n factor, and this is where the factor is lost. You can perform this in a different way and you can afford to not lose this log n factor in the succinct space regime. So I'm not going to get into that. There are other ways you can do it. And the important point is that the space parameters, we set the recursion parameters in a kind of a geometric way so that the space that we use in the entire cover will never exceed this geometric series. So you will actually get a contradiction. You will get a too good to be true covering of the outer dimension. So that's all I'm going to say about that result. So this is kind of the main framework. Do I have like 7 minutes? Or?
Yeah, me too.
Okay, good. So, so we have this result about rectangular matrices. And this already, we showed already would imply, if you prove like a log 2 plus epsilon lower bound, even against very small linear space, you already improved the state-of-the-art rigidity for rectangular matrices, or kind of semi-explicit matrices. But one kind of annoying downside of this recursive argument is that it produces a very skewed matrix, right? Because we only recurse on the column space. We don't know how to recurse on the row space. We never reduce the number of rows in the matrix. So we end up with kind of just to simplify the parameters, the matrix that this recursive algorithm produces, assuming we stop in the last iteration, which is kind of the worst case, is a very skewed matrix. The number of rows m remains what it was, so it's like n to the 10. And n prime can be kind of very small. It's related to kind of the t, the lower bound, the parameter, the lower bound parameter that we began with. So maybe polylog n or something. So the bottom line is that it produces a very skewed matrix, but the rigidity parameters are actually quite good. So in order to decrease the rank below, let's say n over 2, you need to modify, let's say, a constant fraction. You need to modify like almost all the entries, or let's say n over 10 entries in some row of this matrix. Right? So suppose you want to get a square matrix from this. There's one kind of almost trivial idea that will preserve the sparsity parameter and will make this matrix square. What is it? Well, you can just append identical copies, just m over n prime identical copies of this matrix side by side. This will be an m by m matrix. Of course, the rank remains the same, right? We just added identical copies. But the hope is that actually the sparsity parameter, the number of entries you need to change, will actually be linear in M. So it will still be, you'll need to almost modify all of the entries to decrease the rank below N prime. And the explanation is simple, right? I mean, if you want to decrease the overall rank below N prime over 2, then you need to decrease the rank of each block below N over 2, right? There's no other way. And the rigidity of the original matrix, M prime, tells you that you need to modify almost all the entries in some row here, right? There's just one problem. What is the problem?
The rank is low. The rank is low.
That is a problem, right? But that we're not going to solve. So you will prove a rigidity lower bound for a weaker rank regime relative to M. But there's a more problematic issue with this argument. The problem is that these rows that you need to modify may not be the same row. So it could be a different row in each block, right? And this is a direct consequence of working with worst case rigidity. So does it make sense? So we know that this argument tells that any low dimensional subspace has to be T far from some row, but it could be different rows in each block. We don't know how to control that. If we had the stronger property that...
But I don't understand why, because let's say you fix a subspace of dimension n prime over 2.
Yeah.
Right, so let's think of the subspace of the columns, right?
Yeah.
So you know that in the first block, there is some row that you need to change.
So you claim that...
But it's going to be the same,
it's going to
be the same row in all of them, right?
I don't see how...
It's the same matrix. If in one of them I don't change in the first one.
No, but this subspace is, when you project it on, right, it's in...
But think of the subspace of the columns instead of the rows.
No. So that's the point. The subspace is, okay, it's a subspace of the row. So it could be a different
But it's the subspace. I mean, it doesn't matter if it's rows or columns, right?
Sure, it's a square matrix.
So it
doesn't,
same, right?
Yeah.
Think of the size of the columns.
So I think this argument doesn't work. I mean, this is the obvious thing to...
Maybe there could be different ways of different rows you choose to specify.
No, but I'm saying, let's say that in the first matrix, you fix a subspace. Let's say in the first matrix, the first row is far. So the first row in the second matrix is also going to be far.
No, but it's not the same subspace. It's not the same.
But it's the same subspace.
You can pick a different subspace.
Yeah, but you want to for every subspace there is a row that's far. We're going to fix a subspace. By definition, there is a row that's far.
Okay. I think what I meant, if you fix a subspace, project the subspace on the first n prime coordinates. Your guarantees on the original matrix is only against subspaces which are in this dimension.
Think of the subspace instead of the row space as the subspace of the column space.
Sure.
Right?
But then you don't have the guarantees of the
first.
first. Okay.
Anyway.
Okay, let's discuss this offline. All I'm saying is that one thing is for sure. If you had global rigidity, if you knew that you need to change 10% of the rows in each block, or you had to change omega m times n prime trees, then this trick would work fine, right? Because it doesn't matter. It just says that you need to change a lot of entries in each block, right? So what we would really like to do is to perform our recursive algorithm with global rigidity. Unfortunately, all this nice characterization, we don't know how to perform it with global rigidity. We only know how to do it with worst case rigidity. And this kind of annoyed us for a long time. And the nice thing we managed to prove is actually we can just show a completely black box reduction from worst case to average case rigidity, which kind of uses similar ideas to the proof that circuit lower bounds against E imply that BPP equals P. So it's going to use a locally correctable code. So what is it? For the non-experts, what is an LDC? So an LDC is just an error correcting code with the extra feature that every coordinate in the original space, in the original message, can be retrieved with high probability by reading only Q entries, Q coordinates of the code word. Right? So what we show is the following. So let's parse this. We show the following, that if you have a matrix A, which is a very skewed matrix, possibly, that is worst case rigid, right? Then if you apply an ECC, a Q-query linear as ECC, to each of the columns, right? So you can think of the columns as being the original messages that you want to encode. If you apply an LDC to each one of the columns, then I claim that E of A has to be globally rigid. So actually 10% of the rows are going to be far from every low-dimensional subspace, right? And you lose a Q factor here. So that's the point. So 3 minutes. Do you have 3?
Yeah.
Okay, 3 minutes. So the key fact, which I think was observed, I don't know, in a paper by Goldreich, Karloff, I remember the last, Trevisan, and and Schulman, is the following crucial property of linear LDCs, which is not true for general LDCs. The property is the following. It says that if your LDC is actually linear, then any row in the original message matrix A is literally spanned, and so for any row and any 10% fraction of the row of the coordinates in the code word that you corrupt, this row is literally spanned by Q other rows outside this 10%. This is somehow non-trivial. I was hoping to prove it, but I'm not going to prove it. So again, so any row here is, for any row and for any 10% of the coordinates you corrupt, there's always going to be some Q rows that span this row. And now the proof is simple. Suppose this matrix is not globally rigid. So suppose that fewer than 10% of the rows need to modify these many entries. Right? This means just by a Markov argument, this means that the average rigidity of each column you just divide by m is T delta over 2Q. Right? By a Markov argument, this means that at most 10% of the rows here, right, at most 10% are very far. All the rest of the rows of E of A are close just by the contrapositive assumption. This is a simple Markov argument. But this means that any row, right, using this key fact, this means that any row is spanned by those remaining rows, all of which are very close, are T over 2Q close. So so you get the property that literally every row of A, every row is going to be, it's a Q linear combination of close rows. So you get that it's less than T over 2 far. And that's a contradiction to the worst case rigidity of A, because A must have some row which is far from it. So that's it. And luckily we have Reed-Muller codes, which we only lose a logarithmic factor, and I kind of don't have more time for that. We have further implications to the succinct regime and to polynomial data structure lower bounds. But I think the main message is just that these two seemingly very different kind of circuit models are actually the same pretty much in the linear model, which if you try to prove this in the CellPro model, it seems very, very different. It turns out to be somewhat the same in the linear model. Thanks.
Any questions?
So the construction of the rigid matrix given a data structure lower bound is still going to be a T to the NP kind of a construction?
In the linear space regime, the succinct regime, we show that we don't lose anything, so it's fully explicit. So if you improve the state-of-the-art succinct data structure lower bounds, then we can perform, in the succinct regime, we don't lose the log and factor. So literally any asymptotic improvement would give you data structure lower bounds. And it's, actually I think there it's also, it's still semi-explicit. I think it will still only produce P to the NP construction. Yeah, so we don't, because we need to check if we only know how to relate these two notions of inner and outer dimension for a submatrix. And this submatrix kind of have to use an NP oracle to query if it's rigid or not. We don't know how to get around that. So I'd be very surprised if you can literally relate the original inner and outer dimension of the matrix. So I think it's an interesting question, but that would be great to prove that you can literally show that if it has large outer dimension, that literally this matrix, not a submatrix, this one itself has small inner dimension, but I don't know how to prove that. Yeah, so I don't know if I said the last theorem, which I glimpsed over, it implies that in the squared case, if you beat a log cubed lower bound, unfortunately we lose another log factor due to the LDC, but if you prove a log cubed, super log cubed, then you beat the state, then you beat rigidity for some rank parameter. Then you beat the state-of-the-art rigidity, but for the square case, which is kind of what we actually care about. So, yeah, so it's probably not a complete no-go theorem. It's more of kind of a connection. Proving polylog data structure lower bound is still kind of will not imply anything about circuit lower bound.
Staying on me.
Thanks.